Hi everyone. This lecture is going to start out with a discussion of expected values, but expected values in a new context for us, where we have pairs of random variables that are both continuous. There are not going to be any big surprises there, and so that'll go relatively smoothly, I think. After that, we're going to talk about independence, and particularly independence of pairs of random variables. And we've seen independence in a few contexts for this class so far. We've seen it in the first weeks of the class when talking about just individual outcomes or events. And then we talked about some consequences of independence, like what would it mean for expected values of products of random variables or something like that. Today we're going to see how independence can be defined in terms of independence of two random variables, how to define that in terms of their joint probability density function or mass function. And so we'll see that. And then we're going to discuss how do you quantify how dependent random variables are if they're not independent. And we'll sort of see two ways to do this. One way is called covariance. And that way of doing things has a sort of a unit dependence or sort of a dimensional quality to it that is sometimes not really desirable. And then we'll talk about a way to do this without that issue with a quantity called correlation. All right, let's get started. So I'd like to start today with just a reminder of where we were last time, or not so much where we were, but one of the things that we were using over and over again, because we're going to be using it again. So this is a reminder about last time. We used a particular example repeatedly, and we'll do it again. So we had our sort of main example. Which was two random variables. So we had x and y, and they were both continuous. And they had the following probability density function, joint probability density function. So with joint PDF. So it started off like this. So it has this joint probability density function. And it's written in terms of an unknown parameter initially that we called k. And then it's just linear in x and linear in y. And this was for x in the region 0 to 2. And y was in the region 0 to 3. And everywhere else it was 0. So we started off with this example in the last lecture, and we used the honesty condition to show, to find a value for k. So honesty told us that k was equal to 1 over 15, 1/15. And then we also showed, we found the marginal distributions by integrating. So if you integrate this function, the probability density function, over all of y, you get the marginal distribution for x, which looks like this. And so it's also piecewise defined, so it's 1/15 times, better put that in parentheses, times 3x plus 9 halves. So we just found that by doing the integral over all of y. And so this was for x going from 0 to 2 and 0 otherwise. And we also found the marginal distribution for y by integrating the joint distribution over all of x. And the result was 2/15, so write it like this, times 1 plus y. And you can look back at the last lecture's notes to see how this was done. And this was for y going from 0 to 3. And it's 0 otherwise. Okay, now, I mainly just wanted to write these things down because we're going to use them again today. And it's good to just have a copy of them here rather than try to redevelop them. All right, so the next thing we're going to discuss, the first new item on the agenda today, is how to do expectation values for joint, or for the bivariate case of continuous random variables. And it works exactly how you would imagine, I think, especially having seen the case for discrete random variables. So this is expectations, or expectation. And we'll set it up for, I think in the notes this is done for specific cases, and then it's written out in general. We'll just write the general definition. There's no really reason to show the special cases because they fit within the general description. So we say, if you've got these two random variables, so if x and y are continuous random variables and you have their joint PDF, and we'll use the same notation, so it's f of x, y. Then you want to find a way to write the expected value for a particular function of x and y, or for any function, right? The expected value or expectation value for any function of x and y. That we'll call g. Is the following. So it is, we'll write it out here. So the way we write it is the same as before. So it's expected value of g of x and y. And the calculation works like this. So you integrate over all of x, so from minus infinity to infinity over x. And so I'm using my sort of left-hand justified integration notation. And then integrate over all of y. And then we put the value of the function times the joint probability density function. So hopefully that looks exactly as you kind of would have imagined it would. I'm kind of recenter it here. And we'll highlight, so the thing that we're defining here is the expected value for any function. And so hopefully that doesn't look like too much of a surprise. And we could go in just right into using it. So we'll do that now. And we're going to use our previous example. Okay, so here's our example, our new example, which is a carryover of the previous ones. So I want to find the expected value for the product x times y. So we're going to find three expected values. Expected value for x times y. And then I also want the expected value for x and the expected value for y. Now, those two aren't really any new calculation. The expected value for x and y, you calculate those the same way you would ordinarily, but you first have to find the probability density function for x to do the expected value for x, and you have to find the probability density function for y for the y expected value, and you do that by integrating the joint distribution, the joint probability density function, and you call those ones that are single, that have a single variable argument, the marginal distributions, but they really are just like they were before. All right, so let's first do the product one. So the expected value of x times y. So we'll just follow the definition. So it's integrate over all of x, and then integrate over all of y. And then the value of the function, which in this case is just x times y, and the joint distribution function, which I'll write now, or joint density function, I'll just write it in its generic form here, like this. And so in the next line, we're going to make use of what the joint probability density function looks like, and it's over here. So it's 1/15 times x plus y, so it's this thing here. And it's only non-zero in the region x goes from 0 to 2 and y goes from 0 to 3. So we're going to make use of that. And so that's going to make our integrals a little simpler. The 1/15 can come out in front. And so I have integral from 0 to 2 in x, and integral from 0 to 3 in y. And I have x times y, so that was there, that's the carrying over the factor in front of the f there, times x plus y. All right, so that 1/15 x plus y is the joint density function. All right, and so now we'll just go ahead and do this. Now it's just an integration problem. So 1/15, leave the x integral alone for now. And we'll let's just make the integrand look a little simpler by distributing the x times y. So I've got x squared times y plus x times y squared. All right, and now I'll do the y integral. Right, and so we've got integral of y, so the x squared is treated just as a constant going from 0 to 3. So this is x squared, nothing happens to that, and we get 1/2 3 squared. So that's 1/2 9. I just want to leave it there so you can see it, how it came about. Plus, and then again, that nothing happens to the x here. The integral of y squared is 1/3 y cubed, and that goes from 0 to 3, so that's 1/3 3 cubed. Yeah, and we'll clean that up and then we'll perform the x integral. All right, so that's 9/2 x squared. And then, so one of those threes cancels and we just get 9x. Yeah. All right, and now we can just do the x integral. The 1/15 is still sitting out here. And the integral of x squared is 1/3 x cubed, and it goes from 0 to 2. And so this is, so 9/2 times 1/3 2 cubed. Right? And the integral of x is 1/2 x squared, so this is 9 times 1/2, and it goes from 0 to 2, so this is 2 squared. Right? Now we just have to tidy things up a bit more, so just do a little bit of rearranging. 1/15, and then let's see, the 3 goes into the 9 3 times, and you lose one of the 2's, so you get 3 times 4, so that's 12 for the first term. And then you lose one of the 2's here in the denominator, so you get 18. And so that's 30 over 15, famously called 2. All right, so that's the expected value for the product x times y. It's 2. All right. And now we'll do the expected value for x. To do this, we need to use the marginal distribution. So it's the integral from -infinity to infinity. It's the integral over all x of x times the marginal distribution, also known as just the probability density function for x. And I'll switch back to ordinary integration notation here because there's only one variable. There's no benefit to switching to the other way. And so now I have to go back over here and find the marginal distribution, which we had, marginal density function. And I'm just going to copy it. So it's 1/15 times 3x plus 9/2, and that's what it is from x goes from 0 to 2, and otherwise it's 0. So we'll go back down here. And so the integral is now only going to go from 0 to 2. And we have x times the marginal density function. And the integration is with respect to x. Right, and so we just rearrange, so 1/15 is out in front. And I've got integral from 0 to 2, 3x squared plus 9/2 x. And now we can do the integrals. So x squared, the integral of x squared is 1/3 x cubed, and that goes, so we've got 3 times 1/3, and it goes from 0 to 2, so that's 2 cubed. And plus we got 9/2, and the integral of x is 1/2 x squared, and so we'll write this as 1/2, and then x goes from 0 to 2, so that's 2 squared, like that. And so lots of things are going to disappear here, so we got 1/15. The 3's go away, and so we just get 2 cubed, so that's 8, plus, and now the 2's go away, so that's 9. And so that's 17/15. Right? So that's the expected value for x. Right, so we've found the expected value for the product of x times y. We found the expected value for x. And then we'll finish by finding the expected value for y. And again, we're going to have to steal the marginal density function. So it's the integral from -infinity to infinity of y times the marginal density function for y. Right, and so let's go up there and steal it again from the previous example, meaning last lecture's example. So it's 2/15 1 plus y when y is in between 0 and 3, and otherwise it's 0. So the integral is going to only go from 0 to 3. Right, so we get integral from 0 to 3. And I've got y times the thing I just copied. Move it over. Whoa. I don't know what I just did there. That was interesting. And we're integrating with respect to y. Okay, so that's 2/15 out in front. Integral from 0 to 3 of y plus y squared. And these integrals we've now done 5 or 6 times. 2/15. This becomes 1/2 times 9. And then this one becomes 1/3 times 3 cubed. So I'll write it that way because we're going to lose a power of 3 there. So we get 2/15 times 9/2 plus 9. And so now we'll bring out the common factor of 9, so that's 18/15 times 3/2. And so we get 9/5. All right. So those are our results for those expected values. It's a lot of algebra or a lot of calculus or however you want to say it, but it demonstrates how you use these things. Okay, now we're going to get to what I think is maybe the more interesting part of the chapter, which is a discussion of the meaning of independence. So independence. And we're going to introduce some new statistical quantities. So the idea here is, if you remember back from chapter 1, so way back in chapter 1, so recall from chapter 1. That's when you first saw the word independence. The definition looked something like this. So you said that events, so you had events A and B, right? So each of those events is a subset of outcomes. They're called independent. Under what we say is if and only if their joint probability, so the probability of A and B, is equal to the products of their individual probabilities. The product of A's probability, the probability of A times the probability of B. So if that's true, then, so you can go either way here, right? So if this is true, then A and B are called independent, or in reverse, if A and B are independent, then this has to be true. So that's what's meant by if and only if. I think you've seen that before, hopefully. All right, so either one of those statements implies the other. So what we want to do here is we want to have some similar, we've been kind of using the term independence for random variables a little bit recklessly without, I think, really carefully defining it. And so what we do is, what we want to do now is we want some kind of similar definition for random variables. So we want something similar for random variables. And in fact, we want to do more than just find out if two random variables are independent. We're going to come up on this at the end of the section. We want to also measure exactly how much independent, if they're not independent, how close are they to being independent, or rather, how close are they to being dependent? So we want to have some kind of way to quantify this, not just a yes or no statement, but we want to have some sort of number to say how close are these things to being independent. So we'll do that as well in this section. But so the first thing we're going to do is just straight out just define what it means for them to be independent. So we'll make the analog of this thing for random variables. So we're going to define this. All right, so you've got our two random variables. So if x and y are random variables, and they have a joint probability density or mass function, doesn't matter which. So they can be continuous or discrete. Probability density function or probability mass function. And then we'll call that f of x, y, either one of those. We don't really reference whether or not they're continuous in this definition. Then we say that x and y are called independent if and only if, so we're going to do the same bidirectional kind of definition here. F of x, y is equal to the product of their marginal density functions. Like that. And I think I will skip adding in the definition of the marginal density functions here, so it should be understood what those mean. If not, consult the previous lecture. And this has to be true for all x and y in the reals, for all real x and y. So that's our definition, so let's highlight what is being defined. So really it's just this word. We're saying what it means for these things to be independent. And again, it goes both ways. So if this is true, then we say these things are independent, and vice versa. If this is true, if they're independent, then this statement over here is true. So you can go from one direction, you can go one way or the other. All right, and I'll just make a comment, so a note. So by extension, so I'm going to make two little comments here. So by extension, so if you can say something about whether or not two random variables are independent, you can certainly say something about whether or not many are. So if you have a series of random variables, x1, x2, and so on, up to xn, if all these things are independent, well, they are all independent if and only if, which people write as IFF. I've always found that super annoying. If and only if. It's an important distinction, and I don't think it's worth burying into a tiny little letter like that. You should say what it means. If and only if their joint PDF or PMF obeys something. Obeys the following rule. So we'll say their joint PDF looks like this, or PMF. So it's a function of all of the three values, or all of the values that the different x's can take on. If it really can just be broken apart, like in separation of variables, if you can just write it as a product of a bunch of single variable functions with marginal densities here. Oops. Like that. So in other words, we just extend this definition. We've just extended this definition so that we can say what it means for more than two random variables to be independent. Okay, I want to make one other note or comment. So note. It really is important that the independence kind of only is one way. I'm getting ahead of myself here. Let's just make the statement and you can see what it says. So random variables x and y are independent. If that's true, then it implies that there's a special rule about how their expected values are related. The expected value of the product x times y will be equal to the product of their expected values. Now, I think that's something we've said before. We didn't exactly say what it meant for them to be independent. But this statement is only one way, right? So if these things are independent, then it will be the case that this happens. But if the expected value of their product is the product of their expected values, it is no guarantee that x and y are independent. It can happen without them being independent. So I'm gonna emphasize that by just stating it. So but, and then we'll just copy this and so the reverse statement is not true in general. It can be true, but having their expected values split like that does not guarantee that the two things are independent. So this is different from the statement up here, where if the joint density function splits into the product of two marginal density functions, then x and y are independent. But it is not the case that if their expected values split in that same way, it guarantees they're independent. So we'll see why that is. So we'll do a little proof here. Really what we're trying to do is prove the first statement. So proof. And what we're really proving, so we're proving the right direction part of that note. And we're doing the continuous case. So we go here. There's no real difference in the proof for the discrete case, except everything is sums. So we're going to prove that top line, and by proving it, it should become clear why that bottom line is true, why it's not for sure the case that if their expected values split, that you can guarantee independence. Where independence is taken by definition to mean this statement here. All right, so let's go ahead and work through the proof. So let's say, so we start off with x and y are independent. And that means that their joint probability density function, so again, these are continuous, is the product of their marginal density functions. Right? So let's go ahead and calculate the expected value of the product x and y. Right? And so we get the integral from minus infinity to infinity over x. And the integral, the same integral over y. And we've got the product x times y times the joint density function. Right? But making use of this property here, we can split this into the product of two different integrals. So this becomes the integral over x of x times the marginal density function times the integral over y of y times the marginal density function. Like so. And that is, each of those things in square brackets is one of the expected values. So this is the expected value of x, and the second one is the expected value of y. Right? So now let's think about how come this doesn't work when you go. So that really is the end of the proof. But let's think about, why does this imply you can't go the other way necessarily, or going the other way isn't guaranteed. All right, so look at the left going case. So walk through trying to go the other direction, right? And you'll see what happens. So what happens is, so the idea here is you start off with this statement here, right? So we start off with the idea that the expected value of the product is equal to the product of the expected values, and then we're going to kind of work our way upwards here. So that means that the expected value of the product is equal to this times this, right? And then the hope, if you could go all the way to the left here, is that somehow guarantees this thing, and that f of x, y is equal to the product of f of x times f of y. And so here's how that falls apart. So let's try to copy the different pieces here. Right, so what you're going to find you've got this thing on the left-hand side, and you've got it equal to this thing from the right-hand side. See if I can fit it in here. Does it fit? It does fit, just barely. Right, so you get to this point in the proof. Right, so move this over a little bit, it's a little crowded. Right? Right, so what happens is you get to here. And then, if you're going to prove that the things were independent, then this statement alone has to guarantee to you that this function is equal to the product of these two. But that just isn't true, right? So this does not mean that these things are true, that these things are the product of f of x, y times that the product of the marginal density functions is the joint density function. And if you're having trouble seeing that, let me point out a simpler case. So it could be true that this is the case, that the product of the marginal density functions is the joint density function. That certainly could be the case, but this does not guarantee it. And so this is very similar to a common source of confusion for new students. So this is similar a similar statement. If you have the following two integrals, right? So integral from minus infinity to infinity. The bounds aren't so important here, but let's say you have a function f1, and you integrate over it, and you find that it's equal to the integral over this other function. f2 of x, right? Does that mean that f1 and f2 are the same? It does not, right? If you think about what this means. So this is saying, the left-hand side is saying the total area under the curve f1 is something, and that something is equal to the total area under the curve f2. So both of these two curves have the same total area underneath them, but that doesn't mean they're the same curves, right? I mean, so here's an example, right? So you could have, let's say, this is f1, and it's normalized, right? So it obeys the honesty condition, so that this area is 1, and then you could have another function. I guess I'll use this color, like this, which is the same function, just shifted over, and it has area underneath it of 1 as well. Or it doesn't even have to be the same function, right? It could be some other thing, something that looks like this, right? As long as these three things might all have the area underneath them 1, but they're certainly not the same function. So be careful when you see integrals equal to each other and drawing the conclusion that the functions are the same, the integrands are the same. There is one condition that you might encounter, one situation where you might encounter where it does imply equality of the integrands, and that's when the integrals are equal to each other regardless of the boundaries that you put. So if you had, like, instead of minus infinity and infinity in those two integrals, you had a and b or something, and you could put them wherever you wanted, like for all different values of a and b, then it would guarantee to you that they had the same, that the integrands were the same. So in other words, if they're always the same, no matter what interval you look at, they always have the same area underneath them, then they are the same curve. But in this case, the interval is fixed, and it's all space, and so it's no guarantee that the functions are the same. So I hope that gives you some impression of why having the expected value of x times the expected value of y equal the expected value of their products, that's not a guarantee of independence. It doesn't guarantee that their joint density function is the product of their marginal density functions. It could be the case, but it's not a guarantee. All right, so that was a little bit of a tangent there, or kind of an expansion on what you see in the notes. All right, so we'll do another example here. We'll do a discrete case. Let's suppose you have, so I want to find out if x and y are independent. All right, so here's the question. So are x and y independent if the following is true? And so this is going to be discrete x and y, and so we're going to write down a little table of their probability mass function, their joint probability mass function. And we're going to let y take on 3 different values, and x will take on 2. So these are the y values. And x can take on values of 1 or 0. These are the x values. And let's say these are a third. Let me make that more clear. A third, 0, or a third. Boy, I'm really having trouble with a third. And then if x is 0, we've got 0, a third, and 0. And so we're going to make use of the marginal distributions, so let's write those in. Oops. I'm going to make a little dotted line here. I don't know, I like putting the marginal distributions on the edges. To remind you why they're called marginal. And so if you sum over all of the y values, what you're left with is the marginal distribution for x, right? And so this is 2/3 and 1/3. And if you sum down across the x values, what you're left with is the marginal distribution for y. And again, so I'm summing down this way to get the results. And so this is 1/3, 1/3, so they're all 1/3. And of course, these all add up to 1. Okay, so that's all the information we have. That's all the information we could possibly want, right? So now, the question is it true that x and y are independent, right? Now, let's suppose you had just paid no attention to the previous thing I did, and you worked out their expected values, right? Oops, I want to make this blue again. So let's just look at their expected values. So these are easy to calculate. So the expected value of the product x times y. Right, so this is a sum over all the different terms in the blue table, multiplying x times y, right? So that's going to be, so I'm going to do the top row first. So I get 1/3 times, so how do I write this? 1 times minus 1 times 1/3, right? So that's that first entry. The second one would give me 0 because y is 0. So I'd get 0 times 1 times 0. So I'm not going to write that one down. The third one would give me 1 times 1 times 1/3, so I do get that one. 1/3. And then the bottom row, they're all going to be 0 because x is actually 0 there. Right? So that's it for the expected value of the product. And so this is minus 1/3 plus 1/3, and so this is 0 for the expected value of the product. And now let's just look at the product of the expected values. We can do these individually. And so for these, we work on in the marginal densities, or marginal probability mass functions, right? So we'll work on the x one first. So the value of x here is 1, so we get 1 times 2/3. And then we get 0 times 1/3, and so that's it. The expected value of x is 2/3. And then the expected value of y is, right, so we're going to get minus 1 times 1/3 plus 0 times 1/3 plus 1 times 1/3. Right, so that's all those things. So and those in the end give us minus 1/3 plus 1/3. And so this first term, this second one is 0. And so we get the product of their expected values is 0. So that certainly makes it look as though, makes it look encouraging that, so maybe, I think you can kind of guess where this is going, right? So we did have, so this is trying to see a situation where you might want to do this going the other way. So you've seen that the product of their expected values is the expected value of their product, but it turns out that these things are not independent, and you can find that really easily. So no. And so here's how you see it. So let's just look at the following. So let's look at f of 0 minus 1. Right, now these are just values in the table. Right, so when x is 0 and y is minus 1, that's 0. Right, so this thing has a value of 0. Or did I do that right? Yeah. So this guy is equal to 0. Yeah. Sorry, just checking my steps there. And we see, is that equal to fx evaluated at 0 times fy evaluated at minus 1, right? And so what is that? So we'll go over here and look at these things. So fx evaluated at 0 is 1/3, and fy evaluated at minus 1 is 1/3, right? And so these two, this is 1/3 times 1/3, so this is 1/9, right? So these things are not equal to each other. So x and y are not independent. So So they're not independent, but you might have thought so but if you had just checked the expected values. So x and y are not independent. Okay, so now that we have a definition of independence, what we want to do is work on our kind of last step here, or I don't know, it's maybe more interesting to me. You now know what it means for them to be independent or not, or at least we've now discussed it. So how do we quantify how far away from independence they are? And so for that, we're going to introduce two new terms. One of them is called covariance. So that's like variance, but co. And the other one is called correlation. All right, so we're going to introduce both of these terms. We're going to go through them in order. So we're first going to talk about covariance, and then we'll do correlation. But the whole point of this is, so we want a way, so we want a numerical, we want to quantify, so we want something easy to calculate. Well, I don't know about easy. We want something to calculate similar to like expectation value or variance. Or the variance. So we want something like this that somehow quantifies the independence. Oops, whoa, sorry. Or measures the independence of x and y, or the dependence, if you want to call it that. So not something that just says yes or no, but something that says how much. All right, so that's the idea that we want here. Okay, and so the first term is covariance, and we'll define that and then see kind of how it tells us what we want. So this is covariance. Right, and so we'll just define it and see how it works. Right, so the definition is simple. All right, so we'll say, and hopefully you'll get some understanding of where the name comes from. So let's say you have these continuous, or they don't have to be continuous. If x and y are random variables with known expected values, so we'll say mu sub x is the expected value. I'm going to use those repeatedly, of x, and mu sub y is the expected value of y. Those are a little easier to write. Then the covariance of x and y, which is what we're defining here. That's the term that's being defined. Is written like this. So first of all, you write it as COV x comma y. So it's something that takes two arguments, x and y. And it's defined with the following equation. So it's the covariance of x comma y is equal to the expected value of x minus mu sub x times y minus mu sub y. All right, and so that's the definition. And you should be, now this should give you an understanding of where the name comes from, because if you notice, so note the covariance of x and x, so the same two random variables, what does that look like? So it's the expected value of x minus its expected value squared, right? And we've seen that before. That's the variance. Right, so that's just the definition of the variance of x. We often think of variance as the more important relationship is the expected value of x squared minus the square of its expected value. Well, that's the same thing as this thing here. And in fact, this was the one we started with. All right, so let's just look at some properties of this and we'll try to prove them. There's quite a few little properties here that we're going to look at. All right, and we're going to prove each one of them. So the first property is the following. The covariance of x and y can be calculated in a kind of a simple way as the expected value of their product minus the expected value, the product of the expected values. Like that. Right, so in other words, that's equal to the expected value of x times y minus mu sub x times mu sub y. All right, and let's just prove that. It's relatively easy to prove. All these proofs are pretty straightforward. There's no clever trickery. All right, so we'll just put in the definition of the covariance. I'll just steal that from up here. Oops, that's the covariance of x and x. Sorry about that. I want the covariance of x and y. So let's put that there. And then we're going to expand or multiply out the thing in the argument of the expected value. Right, and so we get x times y minus mu x times y minus mu y times x, and then plus mu x mu y. And then remember that the expected value of a sum is the sum of the expected values, so that's true in general. And so what we're left, we can take this expected value and apply it to each of those four individual terms. So we get expected value of x times y minus, and now here, mu sub x is a constant, so it's expected, so it can come out of the expected value. So I get mu sub x times the expected value of y and then I get mu sub y times the expected value of x, and then plus mu x mu y, right? But the expected value of x is mu x, right? So this is mu x, and this is mu y. And so we have three terms that are the same here. So I've got two negative ones and one positive, and so what I'm left with is the one negative one. So I've got, oops. So I've got expected value of x times y, and then I've got only one leftover negative term, mu x times mu y. And that was the claimed thing, if you look up here. Right, so that's just a simple proof. All right, the second property I want to look at is similar to what we've seen before. I don't think I'm going to prove this part. It's sort of trivial. So if x and y are independent, then it will be true that their covariance is 0. But, and I'm not going to prove that, so proof omitted. You can try it. It's too easy. But if you try to go the other way, x and y independent does not get implied by the fact that their covariance is 0. So this one I'm not putting any proofs for. And property 3 I'll prove. So this one says this is another way to write out, to express covariance in terms of variances. The variance of x plus y is equal to the sum of their variances plus twice their covariance. All right, so we can prove that one relatively easily. So we'll just put this out. So here's the proof. So the variance of x plus y, right? And so to do this, I'm going to just use the sort of more common definition of variance that we use. This is the expected value of x plus y squared minus the square of its expected value. So expected value of x plus y quantity squared minus the square of expected value of x plus y. Like that. Right, and then we'll just expand this and it'll fall apart. Okay, so we've got the expected value of x squared plus y squared plus 2xy, right, minus the square of mu x plus mu y, right? That's the expected value of x plus the expected value of y. Oops. So I get the expected value of x squared plus the expected value of y squared plus twice the expected value of x times y. And then this stuff I'm going to put on the line below. And so I get minus mu x squared. So I'm just expanding that. Minus mu y squared. Oops. And then minus twice mu x mu y. Right? Now this thing here, that's the variance of x. This thing here is the variance of y. And this minus this is the covariance of x times y. And so there's 2 in front of both of those. And so we get what we were after. So variance of x plus variance of y minus twice the covariance. Or sorry, plus twice. Of x and y. Yeah. Which is the thing we were trying to prove. So those proofs, so far, those are pretty straightforward. You just kind of put in the thing that you're trying to prove on, and it falls apart. All right, and then the last property that we're going to say about covariance is that, and this one's kind of an important one. It's important because it identifies kind of a problem with covariance. So let's say you have two constants, a and b, little a and little b, they're both real numbers. The covariance of a times x and b times y is equal to, and then we'll prove this, but it's a times b times the covariance of x and y. And so here a and b are real. And we'll prove this first, and then I'll talk about why this identifies a problem with covariance. Okay, so we'll just put in the left-hand side here. Right, so here's the proof. All right, and so what is this? This is equal to the expected value. And this is using one of the properties above. The expected value of A times X times B times Y, right? So the expected value of the product of the two different things minus the expected value of A times X times the expected value of B times Y. So which property did I just use there? I think that was the first one up here. Yeah. That's this guy here. Right, so I just used that property there. Okay, and just by properties of expected values, the constants can come out of this, right? So this is AB times the expected value of XY minus AB times the expected value of X times the expected value of Y. And so factoring out the AB from both of those terms, this is AB times the covariance of X and Y. So that's the end of the little proof. Now here's why this is a problem. So this is an issue. I mean, I don't know if it's a problem exactly, but it's a concern. So the whole idea behind inventing this covariance thing, the reason why we've done this, is we want to somehow quantify how dependent or how independent X and Y are. So we would like it to give us, so it's nice that like it's 0 if they're independent. And if it's not 0, they're not independent. But how not independent are they? We would like an answer to that. And so if it's like 90, what does that mean? Can we somehow understand what is the meaning of the number 90? If their independence or their covariance is 90, does that tell us something about how independent they are? Like if we look at two other variables and we find that their covariance is 1,000, are those somehow less independent or more independent than the ones that had a covariance of 90? And the problem here is we don't really know. And the reason for that is that, let's suppose that X and Y were physical things. Like let's suppose that X were a length and Y were a time. Then if you just change their units, so instead of using like meters for the length, you switch to inches, then that's like scaling X by some number, little a, right? Where a is the conversion from inches to meters or whatever. And then you do the same thing for Y. So what did I say? Y was a time. So maybe we change from measuring it time in years to measuring it in milliseconds or something. So then B is going to be a number very far away from 1. And we'll rescale Y accordingly. Then their covariance is now going to be a very different thing. It's A times B times the covariance. So another way to say this is that the covariance has units. And the meaning of those units obscures the fact that there are units there, obscures the meaning of the covariance. So here's the problem, right? So from property 4, the one we just saw, change of units for X and Y, or even just for one of them, changes the covariance. This is a thing that comes up often. You really want to work with dimensionless quantities, things that are immune to changes in units, and this is just not one of them. And so we want to kind of fix this, right? And so that is the origin of this new thing we're going to introduce called correlation, and then we'll stop the lecture with this one. So this is correlation. And correlation fixes this, right? And we'll just state it, and then we'll say some properties, and then we'll be done for today. So what we want to do is we want to quantify the independence of random variables without that issue that was just mentioned above, without issue of units. Maybe I'll just put that. I'll just leave it like that. And so here's how you fix it. So here's the definition of correlation. And I should point out there are other definitions that you might run into with correlation, so you should be a little cautious with that. But here's the definition we're going to use. So the correlation of random variables x and y. It's written as rho, the lowercase Greek letter rho, x comma y. Move this up a little bit. Where it's defined with this following formula here. So rho of x comma y. This is equal to the covariance. So it's defined in terms of the covariance, divided by the square root of the variance of x times the variance of y. And so having that square root down there will fix our problem with units, so that if you change the units of x and y, you will change the value of the covariance, but you'll also change the values of the two individual variances by the same amount. And so you won't change the correlation. So it's dimensionless in that way. So that's nice. All right, and so let's just state its properties. So properties. Let's see, so I should probably put maybe like a zeroth property here. It's dimensionless. So you changing units doesn't harm it. So that's the kind of key thing we were after. That's not in the notes, I just wanted to point that out. So property 1, this is just a naming convention. If rho is positive, then we say you have positive correlation. This is not really very exciting. It's not a surprise. If rho is positive, you say you have positive rho. Similarly, if rho is negative, you have negative correlation. Sometimes that's called anti-correlation. If rho is 0, you have no correlation. That's just some terminology that you should know. Property 2, which I'm not going to prove here, but it's an important one, is that rho is always in between -1 and 1. So proof is omitted. In the notes, there's some funny entry here. It says proof in rice. I don't think that's a reference to the food rice. I think that's some kind of a typo. Or not a typo, rather. I think it's referring to a reference, a book. Okay, so 3, the third property. If x and y are independent, then that does guarantee that rho, that their correlation is 0. But the reverse is not true. Much like covariance and much like independence that we saw before. And the last property for so this one's kind of an important one. If x and y are linearly related, right? And so what do I mean by that? I mean that if y is equal to a times x plus b, where a and b are real, and a is not 0, right? Because that kind of changes that statement significantly. It would say that y is just a constant. So if that's true, then the following row of x comma y is equal to, sometimes you write this as the signum SGN of A. That is to say, it's equal to 1 if A is positive and minus 1 if A is negative. And this one, we're not going to prove it, but it's in your examples sheet. So proof, or you're asked to prove it. So that's question 4 of problems this week. And you can find that on our website. All right. I think I'm going to do one little example, and then we'll call it a day today. This lecture is a little bit on the long side, and you might want to separate it out into more than one piece. Okay, so we'll finish off with this little example. Then I really will stop for today. All right, so we're going to again use the previous example. Right? So for previous examples, so that's the thing I started with at the start of the lecture, where we stated various different density functions for two continuous random variables, x and y. I want you to find the covariance of x and y, and I want you to find the correlation of x and y. Right, so that's the goal. The covariance is pretty simple, right? So covariance of x and y. Right, so that's the expected value of their product minus the product of the expected values. And if you go way back to the start of the lecture, let's find those. That's the very first thing we did in the lecture today. We found the, sorry about all this scrolling, I think that's probably hard on the eyes when you're watching this. So we found the expected value of their product. So this is a long calculation we did with a bunch of integrals, and that was 2, right? And then we found the individual expected values, so 17/15 and 9/5. So we'll go back down. So those are the expected values that we need, right? Okay, and so this is equal to 2 minus 17/15 times 9/5. And if you are good with your algebra and fast, this is, or your arithmetic, or however you want to call it, this is 1 over 25 minus 1 over 25. So these things are anti-correlated. Well, we'll see about the correlation in a second. And their covariance is 1/25. But that doesn't tell us very much, because if we just change the units of x and y, we can change, I think you can't change the minus sign, but you can change the 1/25. So you could make it 1,000,000. And what does that tell you? So we're going to look at the correlation. So the correlation, this requires 2 calculations that I'm going to skip. So to compute this, you need to compute the expected value of x squared and of y squared. And I'll skip those because they're nothing new to us. So the expected value of x squared, you can do that. You need the marginal distribution of x, which we have above. And what you'll get, and you'll see this calculation done in the notes, what this is 8/5. And that tells you that the variance, when you use the expected value of x, you can then find the variance of x is equal to 71 over 225. Okay? These are just things I'm telling you. I'm sort of skipping details. And the expected value of y squared, you can calculate using the marginal density for y. So I'm skipping the details. that's going to be equal to 39 over 10, also called 3.9. And that's going to tell you that the variance of y, so then you can calculate the variance of y using the expected value and the expected value of y squared. This will be equal to 33 over 50. Right, so if you have those things, which you can work out, and you'll see it in the notes if you want to see the details. Those are not new exercises for us. Then rho of xy, so the correlation, is equal to the covariance of x and y divided by the square root of their variances, right? So variance of x, variance of y, all under a square root. And so what that's equal to then is minus 1/25 over the square root of this long thing, right? So 71 over 225 times 33 over 50. And it doesn't turn out to be something super clean, like minus a fourth or something like that. It turns out to be approximately equal to minus 9%. So they're anti-correlated with a correlation of magnitude 9%. So that means they're 9% correlated. And that's a significant number because you can't change it by just changing the units of x and y. That's fixed no matter what units you use for x and y. All right. I hope you guys now feel a little bit better about how one defines independence for pairs of random variables. And in cases where they aren't independent, that is to say, when two random variables are dependent, how do you quantify how dependent they are, how much dependent they are, how do they depend, how much dependence do they have, whatever all that means. I hope you feel better about that. And I hope you're ready for our final lecture, which will be our next one on random vectors. Until then,